I am absolutely thrilled to have you here today because we are looking at one of the most mind-bending, extreme, and literally brutal concepts in all of modern astrophysics. Okay, let's dive into this. Today, we are venturing into the deepest, darkest corners of the cosmos to talk about gravastars. It is a theoretical object that is rightfully dubbed the black hole's evil twin. Over the next few minutes, we're going to explore a cosmic heavyweight that challenges basically everything we thought we knew about the limits of gravity, matter, and the very fabric of reality itself. So let me ask you, what could possibly kill a black hole, right? For decades, black holes have been the undisputed heavyweights of the universe. No competition. They're the ultimate devourers, inescapable gravity wells that just swallow light and matter without a trace. But physicists have theorized that something else might be lurking out there in the dark, something so indestructible, so utterly extreme, that it might just give a black hole a serious run for its money. Think of these theoretical objects as indestructible cosmic soap bubbles, but instead of a delicate little film of soap enclosing a pocket of air, they are unimaginably dense spheres filled to the absolute brim with pure, unadulterated energy. Now, to get something this wild, we have to start with stellar death. When incredibly massive stars finally run out of fuel, they go supernova. It's the ultimate cosmic light show. And we normally expect one of two standard outcomes from this massive gravitational collapse, right? Either the star's crushed core becomes a superdense neutron star, or the collapse is so unstoppable that it completely breaks reality, creating an infinitely dense singularity, a black hole. But what if nature has a third option? What if the intense gravity and the bizarre quantum mechanics at play during a supernova actually forge an entirely different kind of monster? Well, this third option would be born in a violent fraction of a second. Instead of collapsing all the way down into a single point of infinite density, the star's core is just ground down. Imagine a cosmic hydraulic press, pulverizing matter so completely that the particles themselves actually lose their structure and transform into pure, raw energy. This sudden transformation creates a sort of internal mini-universe bubble that violently wants to expand outward. But meanwhile, the rest of the unimaginably heavy star is still rushing inward at incredible speeds. It's the ultimate cosmic clash, an immovable object meaning an unstoppable force, forging something completely unprecedented in the fires of collapse.
When that titanic collision suddenly stops, what's left behind is truly bizarre. A gravastar could theoretically exist at almost any mass, but if we picture a typical one formed from a stellar collapse, it would be roughly the size of the London metropolitan area. Think about that for a second. London. Yet packed into that relatively tiny, contained space is the mass of about 10 of our suns. It's an incredibly dense, incredibly dark sphere just sitting quietly in the vacuum of space, hiding an absolute maelstrom of forces just beneath its surface.
And its exterior? It sits at 0.000000001 degrees above absolute zero. Yeah, you heard that right. It is quite literally the coldest thing in the universe. To put that sheer absurdity into perspective, if you looked at a gravastar in deep infrared, the cosmic microwave background, the fading residual heat from the Big Bang itself, would actually glow bright and warm in comparison. The surface of this object sits at a thermal standstill, completely frozen in an environment that is already unimaginably cold. And this brilliantly illustrates why it can maintain such an impossible temperature. This shell isn't actually made of normal atoms. Not at all. It's forged from an entirely new, unnamed extreme matter, pushed to the very absolute limit of physical laws. It's so unfathomably thin that a standard atom would look genuinely gigantic sitting next to it. And yet, because it was forged by those two extreme forces of stellar collapse and internal expansion, the tension is absolute. Get this, if you somehow managed to hook onto this shell and wanted to stretch it by just 1 single meter, you would need to harness the energy of an entire supernova to do it. No way around it.
Okay, so that's the bizarre outside. But the inside? It breaks our brains even more. The interior of a gravastar is essentially super-dense nothingness, a perfect vacuum. There isn't a single atom, stray particle, or wave of light to be found. It is entirely, perfectly empty. But, and this is the incredible paradox of quantum physics, this completely empty space is simultaneously boiling with the most primitive, fundamental energy in the universe. Nothingness, it turns out, is incredibly heavy.
Think of it as the fundamental ocean at the bottom of reality.
In quantum mechanics, particles like electrons or photons aren't really solid little spheres. They are waves, and you can't have waves without water, right? In the cosmos, that underlying invisible fluid is the vacuum itself. It permeates absolutely everywhere. Even when there are no particle waves actively traveling through a specific patch of space, that fundamental fluid remains, and because of quantum fluctuations, it possesses its own inherent restless energy.
Now, the normal space in the room around you right now is mostly made of this vacuum fluid, carrying a very low inherent energy. It's calm, peaceful. But inside a Gravastar, it's an entirely different story. During the star's initial collapse, the universe acted like a giant cosmic pump, compressing as much of that vacuum fluid into the core as the laws of physics will mathematically allow. The result? An interior vacuum that has almost a billion trillion times more energy per cubic centimeter than the empty space outside. It is literally nothingness pressurized to the absolute breaking point.
So the absolutely crucial point here is that a Gravastar is an eternal stalemate. Inside, an ocean of compressed vacuum energy desperately wants to expand outward, sitting right at the absolute limit of compression. Outside, it's trapped by an impossibly tight, incredibly cold shell that sits at the absolute physical limit of matter. You have two universal limits locked in an endless wrestling match, perfectly balanced forever without either side giving an inch.
From a safe distance, this perfectly balanced object acts exactly like a black hole. It curves space, slows down time, traps passing light, the whole shebang. But what if you were unlucky enough to fall into one? Well, actually, you wouldn't even survive long enough to see that impossibly cold shell. You'd be ripped apart by immense gravitational tidal forces, spaghettified and ground down to your fundamental atoms long before impact. Once your scattered remains finally touched that impossibly hard surface, they would instantly dissolve, breaking down and simply converting into a tiny bit more vacuum energy to feed the interior.
Now you might be wondering, why are physicists dreaming up this wild stuff? Is it just cosmic science fiction? Not at all. Gravastars were actually proposed as a much-needed mathematical band-aid. For decades, black holes have completely traumatized physicists because of the nightmare hiding at the very center, a singularity. You see, the deeper we dig into the math of black holes, the more they refuse to play nice with the rest of our understanding of the universe.
Black holes rely entirely on singularities, these infinitely dense points with zero size. Singularities literally break our best understanding of physics. They create points where the math just spits out infinity and completely stops working. Worse, they seem to permanently delete information from the universe, which is a huge no-no, violating a core tenet of quantum mechanics. Gravastars, on the other hand, offer an elegant mathematical escape hatch. Because they feature a physical shell and a super-dense vacuum interior, no singularities are required. The math continues to work smoothly, and cosmic information is saved.
But actually scratch that. It's not a perfect fix. As with all cutting-edge astrophysics, we're just trading one mystery for another. Gravastars create new problems of their own. To fix the black hole paradox, we have to accept the existence of that weird, unnamed exotic matter to build the shell. We have to buy into the paradoxical concept of superdense nothingness carrying immense mass. They work brilliantly on paper to resolve the singularity issue for sure, but they rely entirely on extreme cosmic building blocks that we haven't actually proven to exist anywhere in nature yet.
So how do we prove they exist? How do we find something that looks and acts exactly like a black hole? Well, the key lies in listening to cosmic music. When unbelievably massive objects collide in deep space, they send out gravitational waves, literal ripples in the fabric of space-time traveling out at the speed of light. If we listen closely enough with advanced detectors right here on Earth, we can actually hear the acoustic difference between a black hole and a Gravastar. Because standard black holes have a point of no return, an event horizon, two of them colliding sounds kind of like a bass drum. It's a deep, massive thud that stops abruptly because the event horizon instantly swallows all the vibration. But a Gravastar, it has a physical solid shell. If two Gravastars smashed together, it would sound like a gong. The physical matter vibrating intensely against itself would leave subtle, ringing echoes in the gravitational waves trailing right behind the initial crash.
So why haven't we heard these cosmic gongs ringing through the universe yet? Well, right now, the signal is simply swamped by gravity. The gravitational pull around these immense objects during a collision is so overpowering that it muffles the delicate music of the impact. It's exactly like trying to tell two different musical instruments apart while listening to them play through a thick concrete wall. Our current gravitational wave observatories are incredibly advanced, but we are right on the technological edge, just not quite sharp enough to pick up those subtle echoes yet. So as we wrap up, I want you to keep chewing on this central question. Are gravastars real, or just a beautiful math illusion? They fix broken theories, they bypass the absolute nightmare of singularities, and they suggest that the universe might be far stranger and more elegant than we ever imagined. Whether they turn out to be real cosmic soap bubbles out there in the dark, or just a brilliant mathematical idea on the scientific discard pile, they remind us exactly why we push the boundaries of reality.